Welcome to the next lecture on frequency response analysis. So, we will see what we have done in the previous lecture. So, for any linear time invariant system g of s which has all the poles on the left hand side of the s plane, which is given the input of a sine wave, we have had the following observations. The first one is the steady state output is sinusoidal, that is what we saw. So, here the steady state is very important because the initial transient part we are ignoring, which is due to the poles of the g of s, and then the magnitude of the output sine wave depends upon the amplitude of the input sine wave and also the magnitude of the complex number g of g omega, and the phase difference in the angle between the input sine wave and the output sine wave is depending on the phase of the complex number g of g omega. And one more thing why we are more interested in sine wave is that any analog signal can be represented as a sum of sine waves, which is given by the Fourier transform, but let us just have that concept for now. We do not need to really go into this thing for now, and these are the formulas we have got for the magnitude of the complex number of g of g omega and the angle of the complex number g of g omega again. So, we have asked a question in the lecture 1 and asked you to try it by taking a Laplace transform and also by simulating. So, a similar example is taken here where the angular frequency is given by 0.05 and the transfer function is nothing but 1 by s square plus 1. So, if you can see here, and when we obtain the inverse Laplace transform, what we would get is like we will get two sine waves in y of t. So, one with the angular frequency like 0.05 and other with angular frequency 1. So, if you could see here there are two waves actually. If you can see, there is a dominant wave and then there is another wave above it. So, these are all like two sine waves, one sine wave is superimposed on the another sine wave, that is what this will give. So, basically if you can in the Laplace plane you will have like 4 complex numbers, and if you invert this into like again y of t, you will get like 2 sine waves, that is what. Now, we will talk about the units in which we will measure the magnitude and phase. So, the magnitude, when we say magnitude, it is the magnitude of g of j omega, which is nothing but the multiplicative gain that we add to the sine wave. So, if the input sine wave is like a sine omega t, the output steady state sine wave is going to be some a sine omega t plus phi into magnitude of g omega, and so this is what we say magnitude, and we are going to use a special unit called decibel by which we are going to represent this magnitude. So, this is a number which is a gain and we are going to use decibel to measure it. There is a reason to do it like this, and like the deci is like 1/10 and bell is a unit which is named after Alexander Graham Bell, and it has its roots in like when they were trying to do the communication etc. They were trying to come up with this unit, and this represents like the power of sine wave in electrical systems. So, but let us not go deep into it. So, what now we are going to understand is like basically the magnitude is represented by the decibel unit, and decibel unit is nothing but taking the log of this magnitude and multiplying that with 20. So, 20 log to the base 10 of the magnitude of g of g omega is the decibel of it. So, why we are going for such kind of measurement, such kind of units. So, basically let us say the magnitude is like 1 followed by 5 zeros, and magnitude is 1 and magnitude is like 0.000001. So, while we are telling all these values, this does not make like immediate sense to us, right, but if we can convert it into 20 log, see if you do it a logarithmic unit, then basically we shrink the values and we can easily feel like 100 dB, 0 dB and minus 100 dB. So, these are like easy to also have a intuitive sense when we work with logarithmic scale for numbers which are having a wide range. And as we saw, the phase was measured in degrees or radians, so which is related to the lag in time. So, though we call degrees or radians, it is actually we saw that it was related to the time period of the sine wave and of the lag in the sine wave with respect to what fraction of time period it is. So, we saw it in detail in the previous lecture. So, this is the unit of phase. Phase is in either radians or degrees. So now we also came to know that the amplitude and the phase, that is the magnitude and the phase, depends upon the frequency at which we excite a frequency of a sine wave we are giving as the input. So one usual thing is like we can one thing we can ask is like, what if I can plot the frequency in x axis and then plot the amplitude and then the phase in the y axis, and then how am I going to get these graphs, and that's what the normal question that we will have. So we will try that exercise for now, and then since again the frequency is going to be a wide range of frequencies, we will again adopt a logarithmic scale for the frequency, again log 10. So now we will attempt to plot magnitude in dB versus the log 10 of angular frequency, this omega, and phase in degrees, and also the versus the logarithm of the angular frequency to the base 10. So now we are writing a MATLAB code for the same with for system, very simple system like 1 by s plus 1 with tau equal to 1, and we plot it over the frequencies 0.0001 to 100, and then we take the magnitude as 20 log 10 of 1 by square root of, so magnitude of it is nothing but 1 by omega square plus 1. So now tau is equal to 1, so tau doesn't appear here. So basically we get magnitude as this one, and phase is nothing but we saw minus tan inverse omega tau, so it is minus tan inverse omega. So if you can see, if you can plot between the angular frequency and the magnitude, you get this graph, and similarly if you can plot the phase and the frequency, we will get plot like this. So let us understand this in some little detail. So again this is a logarithm of angular frequency. We have plot, this is a logarithm of the angular frequency. So we have plot against logarithm of angular frequency versus the magnitude in decibels. So when we say tau equal to 1, basically we can see the pole is at s equal to minus 1, right. So this is the pole, and if you can see here the magnitude is nothing but 1 by root of omega square plus 1. So if you could see if you substitute the values of omega and see, basically when omega is very less than 1, what happens is this particular term is nothing but approximately 1 by root 1, because omega square, if it is less than 1 we can ignore that, and when omega equal to 1, this term becomes 1 by root 2, and when omega is greater than 1, then it becomes like approximately 1 by root omega square, which is nothing but 1 by omega. So with all this in mind, we can see that when actually before omega equal to 1, we get we get almost the constant amplitude of 1, and when omega is very high than 1, then it actually decreases at the rate of 1 by omega. So if we take the 20 log of the magnitude, then you would probably observe that this value is nothing but 20 log of 1 by omega, or minus 20 log of omega, and if you see here for every log omega, okay, this is a straight line having a slope of 20. So the magnitude in decibels is having the slope of minus 20 for every unit of log omega. So basically the x axis here is log omega, and after omega equal to 1, which is nothing but the frequency, the log of omega equal to 1 is nothing but 0, when log base 10 to the 1 is 0. So after this point, what you can see is this becomes almost a straight line with the slope of minus 20. Then this is log omega, and this is the decibel thing. So this is something that we can observe from this particular plot, and we will be using it a little later in this presentation. And now coming to the phase, if you can see here the phase again varies from like 0 to minus 90 degrees. So again, if you can use the same logic, and then we say tan inverse of omega tau, here specifically tan inverse omega. If you can get this tan inverse omega, and for very low values of omega, tan inverse 0 is 0, and for very high values of omega, the tan inverse infinity is pi by 2. So, this will vary from 0 to pi by 2 or 0 to minus 90. Pi by 2 is in radians and minus 90 degree is in the degrees. So, again if you can observe here like in a just by observing we can say that from minus 1 to 1, okay, this curve is changing, and and this is changing for from 0 to 90 degree. So, basically for every unit of this has to fall like approximately 45 degrees. Okay. So, for every unit it falls by 45 degrees. And also another thing to notice, like omega equal to 0 is where omega log omega equal to 0 is where we have the pole, and this has started falling one unit before that itself. So, when we say 1 unit here, this is nothing but from log of 10 power minus 1, and this is nothing but log of 10 power 0, and this is log of 10 power 1. So, between 10 power minus 1 omega to 10 power 0 omega, which is 0.1 omega to 1 omega, it has fallen by 45 degrees. So, this we call as a decade, like 10 times to get 1 from 0.1 we multiply by 10, right. So, again from 1 to 10 power 1 we multiply by 10. So, this is like a decade. So, 0.1 the units on the x axis is nothing but omega is 0.1, 1, 10, 100 etc. In logarithmic units it will become like minus 1, 0, 1, 2, that is what this is showing. This is log omega scale here. So, this observation also you will be using a little after in this presentation. So, now we have what we have achieved is basically we have achieved plotting the amplitude in decibels and the phase in degrees or in radians with respect to the logarithm of the angular frequency in the x axis. So, this particular plot is called a Bode plot, and this was developed by a person called Hendrik Wade Bode, who was working with Bell Laboratories. And there is a MATLAB inbuilt function called Bode, and you can just feed the transfer function into the particular function and it will display you the Bode diagram. So, whatever we have plotted by doing these calculations manually or like by MATLAB coding, the same figure we can get from the Bode function of the MATLAB. So, this is the straightforward thing to do. So, now based on our observations, let us develop some tricks that we can use without like to draw the Bode plot without any tedious computations. So, taking the amplitude, first we will talk about the amplitude plot, and right now again like we are dealing only with the transfer functions which has poles on the left hand side of the S plane. So, that is something that you have to keep in mind while we are going through these steps. So, for this lecture we are sticking to only that particular use case. So, you can take, to start with, you can take any angular frequency omega, take any value of omega and then find the value of 20 log based on g of j omega. Just substitute the value of omega in this particular complex number and then find the magnitude of it using the formula that we have shown in the first slide. And after every pole, for example, if you have a function like s plus 1 and s plus 2, for omega equal to 1 and omega equal to 2, after every pole you start you add a slope, you change the line to the slope of minus 20 dB per decade. That is what we saw, right. So, after every pole the magnitude was falling by 20 dBs. So, for every pole we add minus 20 dB to the line, slope of the line changes by minus 20 dB. Let us illustrate this. Instead of 2, let us have like 100 here, and then let us have a plot here. So, omega equal to 1 is actually log is actually like 0 in the logarithmic scale, and omega equal to 100 is nothing but 2 in the logarithmic scale. So, what happens is, let us have let us assume that we have computed the gain at some other frequency, say omega equal to 0.1 or something, and then this is a straight line we draw here, and then after this omega equal to 1 we start making it fall by 20 dB per decade, which means that for every unit year, for that is every decade year, it will be falling at 20 dBs here, it will be this will be 20 dBs, and again for every until this point wherein this is like totally 40 dBs, because 20 dB here, 20 dB here, because for every decade it is 20 dB. And then what happens at omega equal to 100 or like in logarithmic scale 2, this starts falling by an extra 20 dB now, because to another pole it starts falling by a extra 20 dB. So basically like 0, 1, 2, and initially it was falling like 20 dB till 2, and then it starts falling by additional 20 dB. So now it falls at the rate of 40 dB per decade. So this is what we can this is a simpler method, which is an approximate method to draw the Bode plot. And similarly for every 0, 0 is something that appears on the like in the transfer function, it appears in the numerator of the transfer function. So for every 0 we increase the slope by 20 dBs. So let us take another example to illustrate this. Let us say like g of s is nothing but s plus 100 by s plus 0.1. So if you draw the Bode, we 0.1 is nothing but -1, and 0, 1, 2 is where this 100 will come, because log of 100 is 2, when it logarithm to the base 10 of 100 is 2. So basically if you can get this one, so at 0.1 what happens is, let us say we computed the value of g of j omega at a particular point before this, and then after 0.1 what happens, it starts falling at the rate of after 0.1 it starts falling at the rate of 20 dB, and at 2 what happens is it starts rising at the rate of 20 dB. So minus 20 dB and plus 20 dB gets cancelled, so this becomes a straight line, it becomes a flat line. Okay. So this is some like it's a tricky way of, it's not a tricky way, but it's a simpler way of drawing the Bode diagrams, and this is mostly used when for some simple transfer functions like this, and this is a very fair approximate thing. And similarly a Bode phase plot is again like let us have a transfer function like g of s equal to k into some zeros and some poles. So for every k, that is if k is positive, then it starts with 0 degrees, and if k is negative it starts with minus 180 degree. So why it is minus 180 degree? Because in the previous lecture you were asked to like see what is the phase of -1, right? So every minus sign contributes to a minus 180 degree phase shift. You can simply think of it like something like this. You have a sine wave and you invert the sine wave, this becomes like this. So the starting of this sine wave is actually like t by 2, like if this is the time period, it starts after t by 2 of the original sine wave. So this is nothing but 360 by 2, which is like 180 degrees. So it's 180 degree phase shift. So now if and then for every pole, let us we observe that it was a 45 degree slanting line which started like a decade before and then ended with a decade after that. And so we start for every pole value, omega equal to a pole value, for example when omega equal to 100, we start a decade before, which is like omega equal to 10 or like logarithm of omega equal to 1, and this is logarithm of omega equal to 2. So at omega equal to 1 we will start dropping the phase by 45 degree slope, and then we will stop it at omega equal to 1000 or like logarithm equal to 3. So basically if you can plot something and then show how it behaves. So at omega equal to 0.1 0.1 is 10 per minus 1. So here is what like okay, for simplicity we will assume 1 for now. So s equal omega equal to 100 is what we are interested. So omega so logarithm of omega equal to 100 is nothing but 2 and 1 here and 0 and 3 here. So the phase is something, it will be like it will be falling when omega at 45 degrees from here until here, and then it will become flat here. So this particular transfer function is having a k as 1 or positive, so this starts with 0 degrees. So from 0 degrees it will go down here, and then after 90 degrees it will saturate. So to get a again mathematical feeling of why this minus 90 degree comes, etc., you can imagine like for example you can imagine something like the angle, phase angle is nothing but given by tan inverse of omega minus omega tau for poles. So, it is nothing but minus tan inverse omega tau, and at omega equal to very small number, omega equal to 0, this becomes like a 0 degree, does not contribute to anything, and then when omega becomes very high, again it becomes like minus 90 degrees. So, every pole will contribute to minus 90 degrees. So, if you have like 2 poles, then it will contribute to like say tau 1 and tau 2, then it will contribute for first pole, it may contribute initially to minus 90 degree, and this pole also will contribute to a phase shift of minus 180 degree when omega is very large. So, let us take another example and illustrate everything together. So, this has zeros at omega equal to 1, omega equal to 10, and omega equal to 0.1 is a double pole, and omega double pole is like 2 poles at the same point, and omega equal to 1000 is a single pole here. So, first let us go through some formal way of doing things. So, first thing we will put everything in ascending order. We will say 0.1, 1, 10 and 1000. If we take the log omega, it is minus 1, 0, 1 and 3 here. So, again, so now if we take the falling amplitude thing, the magnitude plot, then we know that for every pole it falls at minus 20 dB per decade. So, now 0.1 is a double pole. So, for a single pole it is minus 20, for a double pole it will be minus 40. So, minus 40 dB per decade. So, if you can see here from at omega equal to 0.1, which is this line, it starts falling at the rate of minus 40 dB per decade. So, if you could see here, this is like minus 40 dB per decade, and then what happens at 1 is a 0 now, it's a 0 here. So, it gets incremented by 20 dB per decade. So, now this kind of flattens out. So, now this will become until omega equal to 10, this becomes like only 20 dB fall is there, because minus 40 plus 20. So, in this range it is nothing but minus 20 dB per decade. So, this still falls, but at the rate of minus 20 dB per decade. And then what happens at omega equal to 10, omega equal to 10 again it is a 0 here. So, again a plus 20 dB is added here. So, now it becomes 0. So, 0 is a horizontal line. So, there is no slope for this, it is a horizontal line here, until we go to 1000, which is again a pole, and then we will see at 1000, omega equal to 1000, we will have again a fall of 20 dB per decade, if you can see here. So, this is again 20 dB for a decade. Now, this is how you can plot the amplitude plot, and this is if you can see here, if you have drawn a straight line and then you have drawn this, it would have been fairly accurate. And remember, all the physical systems, all the real systems eventually they have a decrease in the magnitude, like there is a limit to which the physical system will actually like can respond. So, very if you go to very high frequencies, all the systems that are in nature will actually decrease the amplitude of the sine wave. That is something that you can keep in mind, which might be useful when we think of more concepts relating to frequency response. And similarly for the phase, if you could see here at omega equal to 0.1, it is a double pole. So, this will start falling at the rate of minus 90 degree, just from starting from before 1 decade. So, from before decade it starts falling at the rate of minus 90 degree, and this actually will try to fall at the rate of minus 90 degree here. But what happens interestingly here is like we have a 0 at omega equal to 1 at this line. So, here the 0 will try to increase it at the rate of 45, because it is single 0. So, this will try to increase it at the rate of 45 degrees, but minus 90 plus 45 is again minus 45. So, this drop is like minus 90, but this drop is like minus 45, and then here again this 45 will continue till again 90. So, the two things are like one decade before and one decade after is what the pole will have effect on the phase angle. So now when it is equal to 10, again it is a 0. So again here it will be trying to rise at the rate of 45 degrees. So if you can see here, this angle here will be 90 degrees. So if you can see here, this in this there is a 45 degree contributed to this 0 and there is a 45 degree contributed to the another 0 at this point. So these at this line this will be an increasing phase angle of plus 90 degrees, and then again at 1000. So after this there is no after this decade there is no effect of this pole on the phase diagram. So this becomes like a constant thing until like 1000 comes, like omega equal to 1000 comes, and at that point it again starts decreasing at the rate of minus 45 degrees for until this point, and then after this has no effect. So every pole or 0 will have effect for a decade before and for a decade after as far as the phase angle is concerned. So that is what you can remember, and you can just draw something, plot it using MATLAB and draw something and then see how whether you are getting this equation or not. It is very pretty simple. And so after this we will answer the question of how. So we have done all this frequency analysis, frequency response analysis, but we haven't talked like how exactly it relates to the process control. So we will try to answer this after a while, after we study more concepts, and you can just play with Bode plots and frequency, different transfer functions with different poles and zeros, and then see what happens. So some questions you can actually think of it like draw the Bode plot of g of s equal to 1 by s, which is nothing but integrator, right? This is the integrator thing. So you can draw the Bode plot of 1 by s, and also try to use MATLAB to draw the Bode plot of what happens when s square plus 0.1 square, and specifically what happens when omega equal to 0.1. You can see what happens when omega equal to 0.1, what happens to the amplitude. So we have previously seen that when omega equal to 0.1 and for such a transfer function it is nothing but resonance. So resonance is nothing but an increasing amplitude. So whether a Bode plot is able to capture this in some way or other, you can just plot it and see. Yes, so these are all some exercises to play around with and to get a better feeling of what frequency analysis is, so that you will be comfortable when we go in details of how we can apply this frequency analysis into the process control. Thank you.